Thank you, Thais, for the introduction. So today I'm going to talk about some recent work with my colleagues Zhenghua Lin from National University of Singapore and my colleague Dehan Kong from University of Toronto. So to start with, the main applied problem I'm going to discuss in this talk is, does getting married help you stay physically active? So this question has been around for a very long time. So here I just find one of those studies conducted more than 2 decades ago. And all the authors concluded that was both men and women experienced a surge in physical activity during the first few years of marriage. They also conjectured the reason for that, but I'm not going into details of that. So in the data was collected in a rather traditional way. They sent out interviewers to visit the participants in the Stanford 5 City project and asked these people about their marital status and the following question. So how do you rate the physical activity you are now getting compared to others of your same sex and age? So with the responses they got, they were able to compare the mean physical activity levels between the married and unmarried groups while controlling for confounders, including sex and age. So this is a rather traditional way. And what we decided to do is to revisit the same question, but using wearable device data. So the data comes from National Health and Nutrition Examination Survey between 2005 and 2006. So in this survey, the participants, instead of asking a question on the questionnaire, they were asked to wear a wearable device called the Actigraph 7164 here during all non-sleeping hours for 7 consecutive days. So this device was placed on an elastic belt. So each participant was asked to wear this device on the right hip all the time, except when they go to bed or when they need to swim or take a shower. So here's the data, what the data looks like during a 7-day period. So here I just randomly chose 2 individuals from the data set. So on the x-axis, you can see that we have a total of 10,080 minutes. And on the y-axis, we have their physical intensity level. And the gap you can see here will be the time when they go to bed or when they take a rest. The one thing you will notice if you look at this data carefully enough is that different people may have different circadian rhythms. So for example, on the right, you can see that this particular individual has a very regular schedule. They sleep and wake up, sleep and wake up, and they repeat this pattern for 7 days. So this is perhaps from someone who's very disciplined. But now if you look at the individual on the left, you can see that their schedule is a bit chaotic, right? So here they sort of stay awake for 48 hours straight and then go to bed and kind of get up and sleep. So anyway, the message here is different people will have very different circadian rhythms. But our goal is to compare them in terms of their physical intensity levels. We're not so much interested in their circadian rhythms. So what we decided to do is to transform the raw data into distribution functions. So on this graph, you cannot see their circadian rhythms, but instead what you are left with is their distribution functions of these physical intensity levels. And the question that we're going to ask is we're going to compare these distribution functions between the married and unmarried groups. Okay, so just a recap of what I've been talking about. So one more point here, which is, of course, you can sort of try to simplify this data even further, right? For example, in principle, you can, instead of using a distribution function as your outcome, you can use their means or you can use their medians. You can summarize them with a single number so that each individual will only contribute a single number to your analysis. But I think you can already see this is not so desirable because we're throwing out a lot of information by doing this. So the question we're really going to ask is what's the effect of marriage on these distribution functions? Just to quickly summarize what has been said, we have an exposure A, 0 for unmarried, 1 for married, and I have outcome Y. The outcome Y is a random distribution function. I also want to adjust for baseline confounders such as age and gender. And my goal is to estimate the causal effect of the exposure A on the outcome Y, but also control for the confounders X. Right, so everything is very similar to the classical setting, except that the outcome y is now a random distribution function. So I will assume people here are familiar with the potential outcome framework. So I will just mention that I will use y parentheses a to denote the potential outcome under exposure a. And in a classical setting, we all know that the average causal effect is defined as the mean difference between y1 and y0, right? So this is something classic. But when we try to answer the same question, but for distribution valued outcomes, the first question, and perhaps this is the major problem we run into, is how do we even define the causal effect if the outcome is a distribution function? So from the definition of ACE, the classical definition, we can see that there are two steps in this definition. So first, we take the average of these potential outcomes, and then the second step, we take their contrast. So on the surface, it seems very straightforward to extend what we have to distribution functions, because we know that distribution functions still take values in the real line, and in particular, it's between 0 and 1. So in principle, we can just take the usual averages and the usual difference. And what we'll call the Euclidean averages and the Euclidean difference. But we're going to see in a minute that this is not so desirable. So we need a better definition of causal effect if the outcome is a distribution function. Okay, so first I will talk about how to take an average. If the outcome is a real number, then this is trivial, right? We all know how to take an average. If y1 is 1, y2 is 3, then we all know that y bar is 2. It's the kindergarten math. Now let's consider a case if y is a distribution function. Let me consider the simple case where these are degenerate distribution functions. So y1 will put all its point mass on 1. So it's a random variable that takes the number 1 100% of the time. And similarly, y2 is a degenerate function that takes the value 3 100% of the time. So what do we hope for y bar in this case? I think because of the example above, I think one would reasonably hope that in this case, the average will be another distribution function that takes the value 2 100% of the time. Right, so that this is at least should coincide with the classical case. And now let's see what do we get if we just take the usual Euclidean averages of distribution functions. So here what I plot are distribution functions for y1 and y2. The blue lines are for y1, so you can recall that this takes value 1 100% of the time. So there's a jump from 0 to 1 at the point 1. The green line is the distribution function for y2. I recall that this takes value 3 100% of the time. So there's a jump at 3 from 0 to 1. So now let's take the average. So this is what we get is these red dashed lines over here. So essentially what we have is below 1 it's 0, above 3 is 1, but between 1 and 3 this is half. So what it means is that it will give us a random variable that takes value 1 50% of the time and takes the value 3 50% of the time. But this is not so desirable because remember our intuition told us that the average of these two distribution functions should take the value 2 100% of the time. And so this only if this is true, we can say our definition on distribution functions generalize what we have if y is a real number. So here's another more complicated, but perhaps this is more realistic examples. So on the left, we have, let's say that our original data is a bunch of number 6. So this is a bunch of images. It's a different ways of writing the number 6. In computer vision, there's a way to transform these images to a bunch of distribution functions. Okay, so now what I want to show you is if we just take the simple Euclidean averages of these distribution functions, and this is what you would get on the right. Essentially, you are just putting all these images on the same place and just average them. This is you essentially get a mess. You don't get anything meaningful. So what's important here is you lose all the structural information about the objects that in the original data. So instead of using the usual Euclidean averages for distribution functions, I'm going to use a notion called Wasser-Sunbury center. This is a notion of averaging distribution functions from optimum transport. So this is based on the concept of a Wasserstein distance, which essentially characterizes the effort of moving one distribution to another distribution. And the Wasserstein-Berry center, which I will use the notation, special notation EY here. No, this is not a usual EY. We have a circle in the middle. This is a distribution that minimizes the effort of moving individual distributions yi to this particular distribution, what we call lambda. So let me try to be a little bit more concrete here. So in our first example, y1 is, remember, recall that this is always 1, y2 is always 3. And the y bar, the Euclidean average will take number 1 50% of the time and number 3 50% of the time. Let's now just do a little bit of a calculation to see what's the f of moving distribution y1 to this to the Euclidean mean y bar. So 50% of time we are moving from 1 to 1, so we're not spending any effort. And 50% of time we are moving from 1 to 3, so distance is 2, so we're looking at square loss. So the effort is 4. So on average, the effort of moving y1 to this to the Euclidean average is 2. So now let's look at what's the effort of moving y1 to delta 2. So recall that delta 2 is a distribution function that puts always point mass at 2. And this is what we our intuition told us that this should be their mean. And the effort of moving from a distribution that takes 1 all the time to a distribution that takes 2 all the time is of course 1. So you can see that the effort we need to move y1 to delta 2 is smaller than the effort of moving y1 to y bar. And in fact, we can show that this delta 2 is indeed the Wasser-Sunbury center. And also for the second example for the images number 6, here we can clearly see that taking the Wasser-Sunbury center, which is the plot over here, this is much better than the Euclidean averages in capturing the structural information in the data. So what we decide to do is to, our choice for taking the average of these mean potential outcomes, since are distribution functions, we're going to use the Wasser-Sunbury center. So mu1 is a Wasser-Sunbury center of y1, and mu0 is a Wasser-Sunbury center of y0. So just to remind you that this mu1 and mu0, they are still distribution functions. Okay, so now I need to define the contrast between these two distribution functions, mu1 and mu0. So again, a naive thing that you can think of is just to take the simple difference as what we did usually to take the difference between these two distribution functions. But I think there are some problems with this naive definition. First, I think this is not very interpretable. We all know what's the meaning of a distribution functions, but what's the meaning of the difference of two distribution functions? And they are no longer distribution functions, so what do they mean exactly? And the second, which I think is, to me, this is more troubling, is that if you define causal effect in this way, then the causal effect is no longer, the average causal effect is no longer the averages of individual causal effects. We have these nice properties in the scalar case so that for any individual I, we can sort of use the average causal effect to approximate the individual causal effect. But if we define the difference in this way, we no longer have this property. So instead of looking at the difference in distributions, what we propose is to look at the difference in quantiles. So under our definition, the average causal effect is a difference in the quantiles of these Wasser-Sunbury centers, mu1 and mu0. And this individual causal effect will just be the difference in the individual distribution functions yi1 and yi0. So what does this measures? So these are functions. Okay, so these are functions, and the argument it takes is a probability between 0 and 1. And let's say if you put 50% here, then what this number tells you is what's the average shift in the median of these distribution functions, or how much marriage has increased your median intensity level. And you can also put in other quantiles. It just tells you what's the average shift in the other quantiles of your distribution functions. So we think this is something that you can directly interpret in a study. And it turns out that if you define the causal effect in this way, then this average causal effect map, the mu1 inverse minus mu0 inverse, will indeed be an average of the individual causal effect, yi inverse, y1 inverse, and y0 inverse. So this is particularly important because now we can use this average causal effect map, which you can compute to approximate the individual causal effect, which we know we don't have enough data to compute. And just as a bonus, you also get that if you define the average causal effect in this way, it's very easy to estimate. So for example, in the standard setting, there are three popular methods for estimating the average causal effect: the outcome regression, the inverse probability weighting, and the W robust estimation. So these are three classical methods to estimate the causal effect. If you're not familiar with these methods, you can just think of this as black box method, where you just take the outcome Y as input, and then you output an estimate. These are three different black box that output an estimate of the causal effect. So for estimating the average causal effect map, we can use exactly the same functional. But now the only thing we change is we replace the outcome Y with this quantile function Y inverse. And everything else remains the same. You can just plug in and you'll get a good estimate. You get we were able to show that you have all the usual properties such as consistency, and you have asymptotic normality. And here is because these are functions, so asymptotic normality will means they converge to a Gaussian process. But the point is, by this simple replacement of you get estimators that inherit all the nice properties of the usual estimators. And this is not so trivial. And in fact, if you try to estimate the causal effect, estimate the mean potential outcomes mu A, then typically we know we have this standardization formula, but this is no longer true if you replace Y with your with your distribution, with a distribution function. It's only true if you replace Y with the quantile function. Okay, so now let me just show you how this works out in this data applications. So in this data set, we have close to 3,000 individuals in each of the married and unmarried groups. So here's a plot showing the Watson Sunbury centers in the married and unmarried groups. And you can see that these are not these are crude comparison, not adjusting for any confounders. So you can see that the black curve for the married group and the blue curve for the unmarried group, they are very similar to each other. So, but the question is, what we want to answer is, we want to adjust for confoundings such as age and gender. So after adjusting for these confounders, this is what we get as a causal effect estimate. So by the way, these are obtained using a W robust estimator. The gray area is the 95% confidence band. So what we can see from this plot. So for example, if you look at go to 0.5 and go to above, you can see a number 20. So what this tells you is that the average change in the median intensity level is 20 units. And the biggest change happens in the maybe perhaps 90% quantile, which is about 50 units. So if you wonder what this quantile means, here on the right, I have a plot that's exactly the same plot as the one on the left, but you transform the x-axis. So here the x-axis is meant to represent mu0. So now what it tells you is that the biggest change happens in the place. The biggest change happens in the place where if the original intensity level is 500. So now after getting married, it will become 550. This is where you'll see the biggest change due to marriage. Okay, so some quick discussions. I've talked about how to make causal inference if the outcome is a distribution function. And I think in many data applications, the data may be summarized as distribution functions. So the example I talked about today is on wearable device, but there are other examples in, say, computer vision or ecology. So I'm not going into details of these examples, but I think you can all imagine that there are many applications where data is not just a number, you observe distribution. And what I hope to convey is that the field of statistical optimal transport is very useful for defining this causal contrast. But I think this is not the end of story. There's still a lot of random objects that cannot be summarized by distribution functions, but instead they may lie on a general manifold. So for example, one may be interested in looking at the causal effect on covariance matrices. Covariance matrices are obviously not distribution functions, but these are symmetric, semi-positive definite matrices. So we can show that they actually lie, this kind of matrices lie on a Riemannian manifold. And there are other examples that I'm not going to talk about. But fortunately, what we can show is that the Wasserstein space we look at today does have a Riemannian structure. So our definition of causal effect maps can actually be viewed as a contrast between the projection of mu1 and mu0, these two Wasserstein centers, onto a tangent space on the Riemannian manifold at a particular point, this uniform distribution. So it's possible to generalize our definition of causal effects for objects lie on a general Riemannian manifold. And a caveat is that there's some difference in the geometric structure between the Wasserstein space and the general manifold. And in general, the difference is that the Wasserstein space is flat, meaning that the curvature of this space is 0. So, but a manifold, of course, may not be. You can have like a unit ball is obviously not flat. So what this means is that, for example, in a asymptotic distribution of the W robustness matter, you will see an extra term due to this curvature effect. So if you are interested in more details, you're welcome to check out our paper on arXiv that has all the details there. So I guess I will stop here and apologize again for the audio problems. And yes, special thanks to Rob for taking over and give a talk before me.
Yeah, very, very interesting. So I have again a few questions, but I would like to open the floor first for others. We can also just cut in later. It occurred to me that it is a very elegant solution, and I can see in particular with this link to the Riemann surfaces, the Riemann manifolds, that it's broadly applicable. However, I am, as a biostatistician, often interact with a lot of doctors, and I would be maybe slightly scared to try to put it a little humorous if I had to explain this causal effect to non-statisticians, so have you any experience in explaining this measure to, say, medical doctors or other people far away from our field?
Yeah, that's certainly a very reasonable question. And I think, so what I like about this particular special case of a one-dimensional Wasserstein center is that we have this interpretation in terms of difference in quantiles. And so, right, so people can, I think this is a concept that doctors can easily understand, right? What's a change in your median intensity? Or what's a change in the 90% quantile of your intensity? Because this may, 90% actually means when you are doing exercise, right? And maybe that represent the intensity of your exercise. And what's the median intensity level? It means it's something that a measure that people commonly use. So I think at the very least, they can, from this plot, they can at least interpret this point-wise. Although, I mean, we would like them to look at this from a global perspective. But at the very least, they can look at this point-wise, and they get this is the change in the quantiles of your distribution functions, of your intensity levels.
Got it. Yeah, thank you. Yeah. Other questions?
So may I have a question?
Yes, go ahead.
Hey, Linbo, this is a very nice talk. It's very interesting that you are dealing with the distributions. So I think that the difference for this with traditional causal inference that is that in the traditional causal inference you have a single number, but you have now you have a distribution. So I'm thinking, can we use something like Monte Carlo method? You draw samples from a distribution and then apply the standard causal inference to estimate the causal effect.
Yes, and in fact, I think in most applications, right, you don't observe the distributions, the functions, right? You only observe what you call Monte Carlo samples from the distribution functions.
Right.
Right. So, to apply our method, actually, you need to go the other way. You need to first estimate this distribution functions from these samples, and then apply this method.
Mm-hmm.
Right. So, I guess your question is, can you just treat this Monte Carlo samples as a vector and then apply the traditional method? Is it more or less what you are thinking?
No, in fact, I do not get the Monte Carlo vectors. I just sample a number from the
a single one number.
Just a sample one number.
Okay. Yes. So yes, of course you can sample one number from the distributions, but I think that's throwing out a lot of information.
Yeah, that would be equivalent to saying I don't want to look at the distribution function. I want to look at, say, the 90% quantile, wouldn't it? That would have been one way of making that reduction into one number. Like
I can,
you said before.
I can look at the mean or median.
Median or whatever, but it would be making a choice on that thing. Yeah.
And you do a lot of samples, and then you can do the average, right?
Yeah, but this is exactly the same as you take the average of the distribution functions.
Mm-hmm.
Well, we are a little bit behind time. I would like to thank all of you, all the speakers, all the audience, and everybody for participating in this. It is amazing what we can do like this. We are saving an amazing amount of CO2. In that sense, we are making the world a better place by having a conference like this. Nevertheless, I would like to add that I really, really, really hope that this conference, which is now on a second year, and I hope and believe it will become permanent. It's really an important conference and more important speakers, but I do hope that the next time will be physically in Beijing. That is so as the very last, please join me in thanking the speakers and yourself, and then have a great rest of the day, however long that might be in your time zone.
Thank you, Tas.
Right. Thank you.